So next, let's look at the graphical method of solving LP problems. And once you formulate the LP model, the next step, of course, is to solve. And as I mentioned, is that there are various methods of solving LP problems. But in this class, we are restricted to use of graphical method. And graphical method is only restricted to two decision variables. So here we'll be working with these two decision variables like x1 and x2. So we have this example here, which is talking about a company which manufactures two types of boxes, corrugated and ordinary cartons. The boxes undergo two major processes, that is cutting and pinning operations. The profits per unit are given there. Each corrugated box requires 2 minutes for cutting and 3 minutes for pinning, for the pinning operation. Whereas each carton box requires 2 minutes for cutting and 1 minute for pinning. The available operating time is 120 minutes and 60 minutes for cutting and pinning machines, respectively. Determine the optimal quantities of the two boxes to maximize profits. So of course, when you're given a story like that, the first thing is to form the LP using the steps that we indicated. So you define your decision variables, and then you define your objective function. Of course, here we are talking about profits, so we must be maximizing the profits. So usually I write it like this. Maximize Z is equal to 6x1 plus 4x2. Then what are our resource constraints? Maybe the best way is to come up with a table that summarizes the information that you are given there. We have two types of boxes, corrugated and ordinary. So we have corrugated and then ordinary. Then we have the resources on this side. Here, mainly we have two resources, which is what and what. We have cutting time, and then pinning time. So when you have a table like this, you'll be able to figure out how the equations will look like. So from the story, we are told that each corrugated box requires 2 minutes of cutting. So maybe I can have more lines like this. It requires 2 minutes of cutting and 3 minutes of, sorry, I should have written down here. And 3 minutes of pinning. Whereas the carton box, hope I have not interchanged them, requires 2 minutes for cutting, 2 minutes for cutting, and 1 minute for pinning. Then you are told the available operating time is 120 minutes and 60 minutes for cutting. So here we have not more than 120. I hope it is visible. And then here we have 60. Cutting and pinning should be like that. Okay, then the profits per unit. Corrugated profit is 6 profit here. And then the other one is how much? Is 4 shillings. So 4 shillings like that. So when you have the table or a table like that, it becomes easier for you to know how the equations will look like. Okay. It makes it very easy for you to know how the equations will look like. I don't know that we have the right equations in the problem. Did I interchange this information? Corrugated box requires 2 minutes. So we have how many boxes do we have? Two types of box. We have corrugated and ordinary. The boxes undergo 2 major processes, cutting and pinning, which is okay. The profits are 6 and 4. Each corrugated box required 2 minutes of cutting and 3 minutes of pinning, which is okay. Okay. Then whereas each This is the ordinary one, I guess so. Each ordinary box requires 2 minutes for cutting and 1 minute for 1 minute for pinning, yes. Then total available time for pinning, for cutting, sorry, is 120, and for pinning is 160. That means you might be having the wrong information here. So what are the constraints that we have in this question? So what is the decision variable? Let's start from there. Let x1 be, and then x2 be. So let's define our decision variables in this case. What are our decision variables in this case?
Cutting time and pinning time.
Really?
Corrugated and ordinary.
Yes. We are in the process of manufacturing we have two products here. So what we don't know is how much of each product to produce so as to maximize profit under some constraints. I think actually we are given that information. So X1 is the number of corrugated boxes. And then number 2 is I think these are the ones that are called carton, so that I don't. That's the other product. So that's what we need. So in terms of, let's allocate this resource. I think there's a problem with the note. So let's allocate the resource cutting time. That's a resource that we have. So what is the inequality, or what is the constraint that represents that? We have less than or equal to 120. That is okay. We have less than or equal to 120 cutting time. So how are we going to allocate it? How is our first constraint? What is our first constraint in this case?
2x1 plus 2x2.
Yes.
Plus
2x2.
2x2.
Less or equal to 120 minutes.
Less or equal to 120. So that's the first resource. So that is that's the first resource. Then the other resource is pinning time. That's the other resource. Let's allocate that resource according to what we have.
3x1.
3x1 plus
x2.
less or equal to 60. Yeah, so I think there was a problem in that question there. So once you allocate all the resources, so of course our profit, our objective function was we are maximizing profits. Z is equal to, which is 6x1 plus 4x2. So like this. Then are we done with the formulation?
Non-negativity.
Yes, correct. You must say that x1, x2, negative. So if you are required to write the model down, this will be of course, we will start here. You let x1 and x2 be as such. Then this is the first part of the model, the second, and the third, and then the last part. So those are the parts that must be visible. So the model is now defined. Okay, so we'll not solve the wrong problem that they have given us. So I want us to solve the equation that we have just written down. So I want us to transfer to another place where we can draw a graph. So this is the model that we want to solve graphically. So we need to plot the resource constraints, including the non-negativity constraints. And then we show what our feasible region is. Then from the feasible region, we should be able to obtain the optimal solution. So how do we proceed? So solve this graphically. Solve this model graphically. So to plot the inequalities, we relax the inequality and we convert it into an equation. So the first constraint after you relax the inequality becomes 2x1 plus 2x2 is equal to 120. So we deal with an equation. So we need to draw that line. But now the inequality will help us shade the appropriate side. So in order to draw a straight line, you just need 2 points. And a convenient way of doing that, you say x and y. You say when x is 0, you find the value of y, and then you also set the other guy. Unless the line is passing through the origin, if you do that, you are likely to get very good points. Okay, so I've decided to start with to only use 0 when x is 0. That is when the line is cutting the x-axis. X is 0 is when the line is cutting the vertical axis, and y is 0 is when the line is cutting the horizontal axis. So when you substitute 0 here, what is the value of x2? Sorry, this is not xy. This is x1 and x2. So when you substitute x1 is 0, what is the value of x2? In other words, when you say 2 times 0 plus 2x2 is equal to 120. So you divide by 2 both sides, you get this is 60. Yes. And you do the same when x is 0. I mean, when x2 is 0, it also means that x1 will also be equal to 60. So the points are 0, 60, and 60, 0. So the line is passing through those 2 points. Okay, so we'll be drawing later. The second constraint, once you relax the inequality, becomes 3x1 plus x1 is equal to 60. So where is the line passing? x1, x2. This is x2. So it's very convenient for you to do that, but you can use any other points. You can use 1 or you can use 10 like that, whichever way. So when I put x1 to 0, then what will be the value of x? x2, sorry.
60.
Be passing through 60. Then when I put x2 to 0, what happens to x1?
20.
So we have the points 0, 60 and 60, 0. So the other 2 points are not problematic.
20, 0.
Sorry, yeah, thank you. 20, 0. 20, 0. I was saying that the last 2 are not problematic because we just shade below the horizontal axis and you shade to the left of the vertical axis. That is what is expected there. So using these points, let's choose a good scale that we'll be using to draw a graph. You can use what scale? 20. Or you can use. Assume these are squared book. So I'll use 2 square boxes to represent 20. Yeah, that means 1 box will represent 10. So of course, I have the option of using my ruler here, but I don't want to do that so that I can save on time. So, but yours, you will be drawing using a ruler. So, but I try to use the lines. So this is 20 for me. This is my x1 axis, and this is my x2 axis. So this is 10. This is 20. This is 30. And 60. Then this is 20. What did I do? I can just use 10 because it looks like 10 will not be very bad. I can use 10, 20, 30, 40, 50, and 60. And these again, I also use the same scale on both axes. 10, 20, 40, 50, and 60. All right, so those are my axes, my x2 axis, my x1 axis. So let's identify the points. The first point is 0. So this is your x1, x2, x1, x2, x1, x2, like that. So the first point is 0, 60. So 0 is at this point. 0 on the x-axis, on the horizontal axis. So that, where is that point, by the way? Is it on the vertical axis or the horizontal axis?
Which one? The X1?
Yeah, this one. This point, 0, 60.
Where they meet.
It's
So where is it?
Where they
X2, on X2, on the X2 line. Because it's saying when X1 is 0,
Mm-hmm.
when X1 is
X2
0, X2 is 60.
Yeah, so it's on the
So
vertical.
when X1, it's on 60, vertical.
Yeah, on the vertical. That's what I was asking. So on the vertical axis. Then of course the other one is on the other side.
Hmm.
We need to connect those two using a straight line. I know you have a straight line, you have a ruler somewhere. See, mine will work. Mine might not be very accurate because of what is happening here. Anyway, let me avoid it. So, but you'll use a ruler to draw that line. Then once you draw the line, usually I shade out the unwanted part, or the part that does not satisfy the inequality is the one I usually shade. So you either shade this side or this side. Okay. So, but how do you know where to shade? You can just pick a point on either side of the line and you substitute that point into this inequality. So now you substitute that point here. Then you check whether the inequality is agreeing or is true or it's false. If the inequality is true, you don't shade that side, you shade the other side where it is not true. And the most convenient point to pick is 0, 0, 0. You pick the point 0, 0 to test. Because 0, 0 is this is the left, this is the right, is on the left hand side of my line. So when I put 0, 0 there, I'll have 2, 0 plus 2, 0 is less or equal to 120. Is that true or false? We are saying 0 is less or equal to 120. Is that true or false?
It's true.
It is true.
It is true. So the side where there is 0, that is the side where the inequality is satisfied. So I shade the side which is not untrue. It will be the same if you picked another point, but you don't need to pick 2 points. If you pick a point like 60, like this is 60, 30, which is on the other side. If you try the point 60, 30, what will you get? You will get 2 times 60 plus 2 times 30, which says that 180 is less or equal to 120. Is that true or false?
False.
This is
False.
false. So that's why I'm shading the unwanted side. So you shade this side. Okay. So let's do the same for equation number 2, the second constraint. So here we need to plot points 0, 60, which you already have. And then we have 20, 0. Easier. Okay. Then you draw a straight line connecting those. Points. Then do you shade the left-hand side or the right-hand side? You pick a convenient point on either side. And 0, 0 will come to our rescue as far as that is concerned. 0, 0 comes to our rescue. So we put 0, 0, which is on the left-hand side. That means 0 plus 0 is less than or equal to 60, which is true. So again, so we're going to shade this side. So we're going to shade we're going to shade that side. Okay. And I think something we are forgetting is to label the equations, the inequalities. So the first one, we call it 2x1. So the first one is 2x1 plus 2x2 is less or equal to 120. So these ones are inequalities. Once you shade them, they are no longer equations, they're inequalities. And the other one is 3x. I can just write here 3x1 plus x2 is less or equal to 60. Then finally, we need to shade for these two. X1 is greater or equal to 0. And where do we shade? We talk about x1 greater or equal to 0. You extend this line like that. X1 greater or equal to 0, you are shading this side. That is the equation x1 greater or equal to 0. And then we have x2 greater or equal to 0. Then you are left with some unshaded parts. That's what you are calling the feasible region. That's what you're calling the feasible region. Okay. So, so once you do that, there are these points, any point of intersection between two constraints in the feasible region. Any point of intersection between two or more constraints in the feasible region is a point of interest. You call those points corner points or extreme points. You can label them A, B, and C. C is up there, the apex. So we have A, B, and C. So point A is which point? X is 0, X1 is 0, and Y is also 0. I mean, X1 is 0 and X2 is 0. Point B is what? X1 is 20.
20.
And the other guy is 0.
0.
And then part C is that, what is this?
1, 0.
0 and
60.
0 and
And
6.
6.
So maybe before we go there, is that now this is what we call the feasible region. I don't want to shade it. Huh? The part I'm calling R is what you're calling the feasible region. In other words, the optimal solution is found there. The optimal solution is found here. One of the points within there. And the beauty of this is that the optimal solution is always one of these, will be given by one of the extreme points or one of the corner points. So one of these will give us the optimal solution. So, but the entire of this region, it contains all the acceptable solutions to the inequality that we have. So that shows all the acceptable. So all these are satisfied within that region. So, but we are looking for when the profits are maximized. So what you do, you can come up with a small table here. when you have your corner points, corner point A, which is 0, 0, B, which is 20, 0, and C, which is 0, 60. Then you evaluate the value of the objective function. Remember, objective function is, it was 6 what? 6x1, 4, 2. So 6x1 plus 4x2. We want to evaluate, because this is profit, we are maximizing that. So you want to see the value of the objective function when you substitute those corner points. So in the first case, Z will be equal to, when you substitute, this will be 6, 0 plus 4, 0, 0. Profit will be 0. Of course, you don't want that scenario. But of course, we are not making losses. The second scenario, when you substitute 20 and 0, it means that you have 6, 20 plus, the other one is 4, 0. So the profit in this case is 120.
20.
And in the last scenario, Z is equal to 6, 0 plus 4, and 1 is 60. It gives us 240. So those are the scenarios. And because we are trying to maximize profits, then this is a scenario that maximizes profit. So the recommendation is produce 0 units of X1 and 60 units of X2 to maximize profits. Of course, this was an extremely simple problem because we didn't have enough constraints. We only worked at the time, because if we put in the other type of resources, maybe the story will be different. But the main thing, that's how you compute, you solve LP using graphical method. Okay, so I don't know either so far any question, because even if there was a mixture of these, if some of them were greater than or less than, the story is the same. You relax the inequality and you work with equations to draw lines. But once you draw the line, you go back to the inequality and shade appropriately. You shade appropriately. And you can just choose 0 to be your convenient point of checking where to shade. 0 is convenient because when you substitute 0 here and 0 there, you will know. It is easier than substituting other and 0 values. And that's basically the procedure of solving such. And that's how you identify the optimal value, the optimal production level. So any question there? So I want you to look at these terminologies as used in linear programming. Of course, the definition is something obvious. I want you to look at what we call a slack variable. We are saying that in linear programming, a slack variable is a variable which is added to a constraint to turn the inequality into an equation. You see, like when we were plotting the graph, we had to relax the inequality. Yeah? Usually for you to relax that, there must be something you are doing for the inequality to disappear. So this is required to turn an inequality into an equality where a linear combination of variables is less than or equal to a given constraint. Okay, like in our case, what we were dealing with, the first constraint was 2x1 plus 2x2 less or equal to 120. Okay, so for that to turn into an equality, then you need to add a slack variable. Then we have a surplus variable, where we're saying in linear programming, a surplus variable is a variable which is subtracted from a constraint to turn the inequality into an equation. And this is required to turn an inequality into an equality where the linear combination of variables is greater than or equal to a given constraint in the former. So we did not have that in our illustration. So we have a slack variable which is added, and then we have a surplus variable which is subtracted. Let me have an illustration so that we can make it very clear, even as you do it later. So let's have this illustration to show how to calculate slack and surplus variables in LPs in linear programming models. So suppose you have this example, which is a minimization type of problem, where you're supposed to minimize that objective function subject to this set of constraints and this non-negative restriction. Okay, so you'll notice that this is a greater than inequality, this one is a less than inequality, greater than and equal to, this one is an equality. Okay, so I want us to introduce slacks. So usually you introduce a slack or a surplus in each of the constraints. So let's denote the slacks or surpluses by, we are going to have one for each one of them. So each of the equations will have, each of the inequalities will have its own slack or surplus. So we have S1, S2, S3, and S4. And maybe the other thing I did not mention is that these slack variables do not alter, do not change the objective function. So let's transform the first inequality into an equation. So in this case, we are going to introduce, we have 4x plus 2y. We want this one to be equal to 20. And we are saying that the left-hand side is greater or equal to 20. So what can make it an equality? In that case, we need to subtract something. So there we're going to subtract 1. Because the left-hand side is either greater or equal to 20. So it's either 20, 21, 22, 23, 24, like that. So for us to make it 20, then we must subtract something, which we are calling S1. This S1 can be 0, but cannot be negative. Then for us to do this, to convert this into an equation, we are going to have minus 6x plus 4y. We want this one to be equal to 20. Sorry, this is equal to 6. We want this to be equal to 6. And we are saying the left-hand side is less or equal to 6. That means can be 6, 5, 4, 3, 2, 1. Okay. So how do we make it 6? In this case, we must add. This is the second one. So the first one we put a subscript 1, second one we put a subscript 2. So the third one we put a subscript 3. And in a similar way, we are going to convert this one. So this will be x plus y. We want to make this one equal to 4. And we are saying the left-hand side is greater or equal to 4, meaning that it is either 4 or 5 or 6 or they all like that, increasing. So for us to bring it to 4, we must take away. So minus S3. Then finally, the last one here does not have an inequality. So it is just an equation. So we are not going to have anything here. So we're going to have 2x minus a y is just equal to 2. So there's no slack. So actually we can just remove this. So when you look at that, you see here we have taken away something. And also here. But in this second case, we have added. So between S1, S2, and S3, which ones are slack variables and which ones are surplus variable based on what we have discussed? Based on this.
S2 is a slack variable,
Mm-hmm.
and S1 and S3 are surplus variable.
Yes, I hope you can see that. The rest, we are saying that a slack variable is a variable which is added to a constraint to turn the inequality into an equation. Okay, and this usually happens when you have a combination of less than or equal to. Okay, so if you do that, you see, if somebody asks you to calculate the values of S1 and S2 and S3, is that very difficult? Because now you say at optimal solution, sorry, here I did not give you this information. We are supposed to solve this problem and then we get the solution. So let's assume that we have solved this problem and then we'll say that optimal solution is given by x is 3 and y is 4. Suppose you have solved this graphically and you found that is the solution. You can try later whether that is true. So if you want to find the values of, to find the values of S1, S2, and S3, you substitute the optimal values of X and Y. You substitute the optimal values of X and Y into each of the equations containing slacks, each of the equations containing the slacks or the surpluses. So in short, if you want to find the value of this variable here, this means that, so you are substituting when X is equal to 3 and Y is equal to 4. So it means that this would be 4 times 3 plus 2 times, this is a 4, minus S1 is equal to 20. So that means the value of S1 is what? It's 12 plus 8, 20. This is 20, right? So this is plus 20 minus S1 is equal to 20. That means S1 is equal to 20 minus 20. So S1 is equal to
0.
0. We do the same here. When X...
Malimo, excuse me.
Yes.
Where are we getting the X3 and the Y4 from?
Yeah, sorry, I said that when you're given a model like this, you need to solve it graphically or using whatever the method. So in this case, we are assuming that we have already solved and we have that optimal solution. You see, like in our case here, let me take you back. In our case here, we got this. We got this. So we are working with a point similar to this.
Got it, got it.
You got it, huh? Now, so we do the same for the second constraint. So here we're going to have minus 6 of 3 plus 4 of what? Of 4 plus S2 is equal to 6. So in this case, what is the value of S2? If you do a quick math, S2 looks like
8.
8. Good. Then in this case, we have 3 plus 4 minus S3 is equal to 4, implying that S3 is equal to
11. 7.
4 minus 7. Is it? No, 7 minus 4.
3.
Which is 3. Now, so if you are asked to compute, yes, if you are asked to compute the values of the slacks and the surpluses, basically that's what you do. Now, if the value of the slack is exactly equal to 0, like in this case, So we say that this constraint is binding. This constraint is binding. In other words, that constraint is passing through the optimal point. You see, like in this graph that we did earlier on, there was a constraint, or maybe several of them, that were passing through the optimal point. This was our optimal point. So any constraint that is passing through the optimal point is binding. So like in our example here, these two guys here, these two are binding constraints. And it means that their slacks or surplus is 0 always. If they are passing through the optimal point, their slack or surplus is 0. And the converse is true. If the slack is non-zero, it means that these constraints are not binding. These ones are called non-binding. Non-binding constraints. Now, the last, I think we did not finish here. This guy here did not have a slack. So we can say that has no slack. That means it has a slack of 0. It has no slack, so its slack is 0. That means it's also binding in this case. Also a binding, it's a constraint here. So in this illustration here, we have two binding constraints. First one and the last one. Meaning that they are passing through the optimal point, those two. They are passing through the optimal point. So if you have been checking the past papers, you have seen some questions asking you to calculate the slacks and so on and so forth. So the thing is, you first solve it graphically, you get the optimal point. Then once you get the optimal point, you introduce this S1, S2, S3 for every constraint. Then you solve for those slacks or surpluses using the optimal point. And then you are able to know whether it's a binding or non-binding. When the slack is 0, when the surplus is 0, that means that that's a binding constraint. Okay. So there's also something else known as shadow price. And usually shadow prices are calculated on the binding constraints. They are usually calculated on the binding constraints. Let me see if I have a good illustration here I can show you. So suppose you're given this linear programming model, you minimize this subject to these 3 constraints there, and then a negative constraint. And suppose you solve this problem graphically or whichever method, and you obtain this is the solution. Then from what you have done, it should be possible for you to obtain the slacks and surpluses for this scenario. And then something that you have not mentioned is write the model in standard form. That means now you incorporate the slacks and the surpluses. Then you obtain the shadow prices. Okay. So let's calculate the surpluses and the slacks for this problem. Then you can tell me what you are going to get. Just calculate and then you let me know what you're going to get us. Because we need S1, we need S1, S2, and S3 for each one of them. So let's do that in 1 or 2 minutes. So once you obtain the slacks and the surpluses, that is your S1, S2, and S3, now you rewrite this model now using equations. Using equations in the constraints, and you also incorporate the slacks here. but the slacks should not change the optimal value. So what you'll do, you'll give them coefficients of 0. So this will be minimize z is equal to 5x1 plus x2 plus 0 s1 plus 0 s2 plus 0 s3. So whatever the value of the slack or surplus, it should not change the objective function. That's why we are giving them 0. Because the optimal solution should not be modified, cannot be changed, because we can't get a better solution than that. Then the resource constraints will look like this now. So we are going to remove the inequalities. We replace them with equal signs. So we're going to have 2x1 plus x2 minus s1 is equal to 60. And the second one is x1 plus x2, this is also minus s2 is equal to 4. And then 2x1 plus 10x2 minus s3 is equal to 20. Then of course, the non-negative constraints remain unchanged. x1 greater or equal to 0, x2 greater or equal to 0, s1 greater or equal to 0, s2 greater or equal to 0, and s3, the slacks must always be non-negative. And the surpluses as well. So this is now what you call the standard form of an LP. That's the standard form of an LP. Okay, so then how do you compute the shadow prices? So the shadow prices are computed using the binding constraints. They are computed using the binding constraints. And basically what you do, you try and, like in our case here, this is the binding constraint that we have, this one, the one with a slack of 0, this one. What you do, you increase the right-hand side of that inequality by 1. You increase it by 1. So that means you're going to have 2x1 plus x2. Then here, instead of 6, we have 6 plus 1, which is 7. Then you make it an equation like that. When you shift that equation by 1 unit, then we want to see what happens to the objective function. The difference between what was there and what we will see is what we call a shadow price. So you solve this simultaneously with, the other binding constraint, which is passing through the optimal point. And in this case, this will be the equation x1 is equal to 0. That's a vertical line. Huh? It looks like this. Huh? Because you have x1 and this is your x2. So I believe that region looks like this. And this is a 0.06. Looks like the one that we solved earlier on. So what we have done, we have shifted this line this way, slightly like that. So now it means that this will be our shadow, this will be our new line. Huh? This is where the constraint, I'm sorry, it's not drawn to scale, but that's where the line will now pass. Then once you shift it like that, you want to see what happens to the value of the objective function. So that's why we are taking 2x1 plus x2 plus 7. You solve with this one simultaneously. You know how to solve simultaneous equations. Already we are having this part. So when x1 is equal to 0, we substitute it here. It means that x2 is equal to 7. So this is like our new optimal solution let me put it like this, new optimal solution. So with that new optimal solution, what is the new, let me call it like this. What's the new value of the objective function? You're going to have Z, let me call it Z new, will be equal to, the objective function was 5x1 plus x2. So this will be equal to x1 is 0 plus x2 is 7. So our new value of the objective function will be 7. So you compare that with our Z old, which is given here. What is our Z old? Our Z old is obtained using the original values. This is 5, 0 plus 6, which is 6. So what we are calling a shadow price is given by Z new minus the Z old, which is 7 minus 1. Sorry, minus 6. So this is our shadow price. That's our shadow price. So in case you ask to compute shadow prices, that's basically how you proceed. Okay, so if you are and you only compute shadow prices for constraints that are binding. And the constraints that are binding have slacks of 0. So these ones are not binding. These ones are not binding. So you only compute on this. If there was another one, you would do the same. Okay. So that is basically it. I think this has taken longer than I expected. I may not want you to fail to learn some of the things. So I was